We're going to skip ahead to the last section of chapter 3. There's quite a bit of theory that we haven't yet covered in this chapter on linear regression. However, I think we've done more than enough to consider ourselves deserving of starting a bit of exploration when it comes to the actual code. We have been coding quite a bit, but it's been just our own examples. Let's see how the book approaches linear regression, starting by looking at these libraries. The library function is used to load libraries or groups of functions and datasets that are not included in the base R distribution. Basic functions that perform least squares linear regression and other simple analyses come standard with the base distribution. We do not need a library. In fact, we haven't been using libraries every time that we use the LM function, but more exotic functions require additional libraries. Incidentally, this is one of the major reasons it's a key selling point in terms of the effectiveness of R. You have all these publicly available, free to download, well documented and accepted by the wider statistical community of functions, data sets. You don't need to create your own functions. What do we mean by creating functions? R doesn't include, and when we say R, I'm referring to base R. Think of what you install the first time that you're actually trying it out yourself. There are your default functions and data. What we're going to do is we're going to load the MASS package, which is a very large collection of datasets and functions. We also load the ISLR package, which includes the datasets associated with this book. So let's do that right now. I'm going to switch to RStudio. We'll have a new page over here or tab. Go into the console, and these are already installed, so I don't need to install them again. Library MASS, and that's loaded over there. Same thing with the package that comes with this book. Let's go back over here. If you receive an error message when loading any of these libraries, it likely indicates that the corresponding library has not yet been installed on your system. Some libraries, such as MASS, come with R and do not need to be separately installed on your computer. However, other packages, such as ISLR, must be downloaded the first time they are used. This can be done directly from within, or what you would do is you would either, if you're going to install a package, you would either go on packages, install, type it over here. And usually you get a list of suggested. So what if I type plot? So these are some of the libraries that include the word plot in their name. Another way of installing is by typing install packages. You need to use these inverted commas. Don't forget that you then need to load the package. So after installing, you do need to actually tell our library and that package without inverted commas then. Yeah. However, the library function must be called each time you wish to use a given package. We're starting from linear simple regression, as we would expect. And we have the MASS library contains the Boston dataset, which records the median house value for 506 neighborhoods around Boston. So let's have a look. I think we have to type data Boston. Let's see. So if we type, if I want to see what are all the different data sets in a specific package, there's probably an easy way of doing it. Probably it's enough to type one line of code, but you can always search for the package over here and click on the name. And yeah, the book wasn't exaggerating when it said a large repository of data sets. Another one is CAS, I think. I might need to install it. It's related to another book, not the one we're using. I think the name goes along the lines of computational actuarial science, something of the same kind. Okay, and this is Boston. The Boston data frame has 506 rows and 14 columns, and you have a bit of documentation over here. Let's see, how do we actually get it in our environment? Can we type, would this work? This doesn't work, does it? No, that doesn't work. Instead, what we need to do is we need to do data Boston, and now that works. You can get an idea of what this looks like by using the structure function. And here we go. We have these 14 variables. So we'll use, if you really wanted to use an entire data set for your linear regression, you would take 13 of them as your predictor variables. For instance, the first 13, and you'd use them to predict the median house value. What are the observations? Or let's get an idea. So we'll type head Boston. This gives us the first 6 records. By default, we have the first 6 records. Now, have they actually, is there no overflow? They've actually all fit in. So we have crime. Let's see. So per capita crime rate per town, the proportion of residential land zoned for lots over 25,000 square feet, proportion of non-retail business acres per town. Anyway, all these different characteristics for each of the 506 observations. Each observation is probably not a county. I doubt there'll be so many counties, but some kind of, we're partitioning. Is Boston a city? Let's refer to it as a city. Certainly wouldn't be able to find it on a map. You could look at your names. You can do question mark Boston, and that's probably going to pull up the same thing that I already have. Question mark Boston. Whoop, question mark, right? Yeah, same thing over there. You can do names, and this gives you a vector of names. And we have the 14 names. Each one is associated with a specific variable. Notice they are all numeric to a certain extent, although I would imagine some of them. That's interesting. What does tax mean? Oh, okay. It's a property tax per 10,000. So that's the annual, or at least I would imagine is the annual property tax that needs to be paid on these properties. We will start by using the LM function to fit a simple linear regression model with the median house value as the response and LSTAT as the predictor. What does LStat represent? LStat is the lower status of the population. I have no idea what that means. Percent. Let's plot them against each other. So plot. Now do remember, if I type MEDV against LStat, this is going to give me an error. The compiler doesn't recognize what we mean by MEDV. Now there are two ways around it. You either fix the data set, which is what the book is doing, and will probably follow suit. If you don't want to fix the data, you type Boston dollar and Boston dollar. So that's telling the compiler, look into Boston and take those values in the MEDV column. And I've swapped these around, haven't I? It's X, Y. Let's have a look. So that's your scatter plot. And you're expecting the data would appear to suggest a negative slope. But what is LStat, right? What is LStat? I guess the book is going to explain, but the lower status of the population, I'm not entirely sure what that means. Does it mean how many people are living maybe below a certain poverty line? Let's see. The basic syntax is lm y regress on x, given the data set, where y is the response, x is the predictor, and data is the data set in which these two variables are kept. Now, this is a lot closer if you compare it to what we've been doing recently. This is a lot closer to a real life example. In fact, I would imagine that this is actual data. If you look at your citations here, it very well one of these papers or books is where the data originally appeared. So let's regress lm, just do lm on its own. We need to fix the data, so that's fix Boston. It is fix, isn't it? Yeah. And now we'll do lm this regress on LStat, and the data is the Boston data. And there we go. You have your intercept and your LStat slope parameter, which is roughly -1. Okay, let's go back. And we have an error over here. Now, one second. The book. Okay, it's just defining it as an object. Remember, everything in R is some kind of object. So you can save your regression. They're using equals. This is when we normally, I guess it's just varying the notation. It's what we normally use as our, we take the arrow to define, and it is lm fit. Okay, and now we have it over here. It's a data object. So you get an error this way. What's the difference between attach and fix? Interesting. They probably do the same thing, don't they? Anyway, ours seems to have worked. We haven't received a data error. If we type lmfit, some basic information about the model is provided. For more detailed information, we use summary lmfit. Let's have a look. So if you simply call lmfit, you get what we had earlier. These are, let's remember, these are our estimated parameters. We only have 2 of them for the simple fact that this is a simple linear regression. If we type summary, then we're going to have more info. And we'll see it like this. You get an idea of your residuals from, I mean, these are the worst, right? The larger they are, the larger the absolute value is. The more the model is doing a bad job of fitting the data. We have our estimated parameters over here as well. Same two that we're looking at. There's standard error. Remember, this is going to be based on the residual. Is it residual? The sum of squares, the RSE. And if you divide the estimate by the standard error, you get your t-value. And these have very large absolute values. So you get an extremely small p-value. Where do we use p-value? P-value is to calculate, to determine whether we reject the null hypothesis. The null hypothesis is that there is no relationship between the predictor variable and the response. And we get 3 asterisks, and that simply means it's really close to 0. So you can reject this. If it's double asterisk, you would reject at that looks like 0.1 cutoff, 0.1% cutoff. This is we're even more, 3 asterisks means we're even more confident. We more confidently reject the null hypothesis than if we only had 2 asterisks. Your residual standard error, 6.214. How is this calculated? It depends on these 504 degrees of freedom, n-2. You have your r squared, your adjusted r squared, which we've never discussed, f statistic, which we've been doing these past few sessions, with 2 degrees of freedom. F statistic, unlike the t statistic, or the F distribution is what I should say, unlike the t distribution, depends on 2 parameters. The number, in this case, those parameters are, I would imagine, the number of predictor variables. This is simple linear regression, so 1. And these 504, which is simply the 506 distributions, subtract 2. And this is exactly what we've just looked at. We can use the names function in order to find out what other pieces of information are stored in lmfit. Although we can extract these quantities by name, example lmfit coefficients, which is usually what I do, right? It is safer to use the extractor functions like coefficient to access them. Interesting. Okay, so it's not something I've ever done myself. Let's have a look. So summary isn't displaying everything stored in the LM-fit. LM-fit is just our linear regression. If you do names, you get a better idea. So there are coefficients, residuals, effects, ranks, all the way up to model, whatever that is. You could get the coefficients by using the dollar symbol, like this, these two. Although the book is saying it is better to use this. I'm not entirely sure why it's better. Maybe we explain why. In order to obtain a confidence interval, for the coefficient estimates, we can use the confint command. Okay, pretty cool. So confint command lm fit. And these are the endpoints. This is 95%. You're ignoring the first 2.5% and you're ignoring the final 2.5% region. You could do it manually if we remember our formulae. You take your estimator and plus or minus to the standard error. I wouldn't mind actually doing it, but how would that work? How do you get the standard error? Because when we had summary, there is the standard error. But if I click LMFit over here, why don't we see it? That's interesting. Does it not appear? I'd be surprised if it isn't here. Although I can't actually see it. So how would you? Never mind. Be interesting to see how you'd actually get these figures without typing them in manually. The predict function, and this is really interesting, can be used to produce confidence intervals and prediction intervals for the prediction of the median house value for a given value of LStat. Let's see. So what we're asking is if LStat is 5, or if it were 10, or if it is 15, what does the model predict in terms of the median value? And I think this is the exact, this is following the model without allowing for any interval. And this would be like maybe a lower bound and upper bound. Again, it would be some kind of confidence interval. Although it's saying interval equals confidence and interval equals prediction. For instance, the 95% confidence interval associated with an LStat value of 10 is between 24.7. These brackets, think of them as the square brackets that we had last year, and 25.63. And the 95% prediction interval is these two. As expected, the confidence and prediction intervals are centered around the same point. a predicted value of 25.05. But the latter is substantially wider. We really don't know what we're saying over here. What is this difference between confidence and prediction? Well, let's do it in R first of all. So we'll do predict. Model object for which prediction is desired. So object is lm fit. And then we're going to give it the new data. Give it to us data frame. We'll say lstat is equal to 5,10. So this is without a confidence interval. This is just the fit. We're making predictions over here. So let's do it this way because it's going to be quite hard to understand what's going on. What we're saying is that the model is predicting, model being simple linear regression. If LSTAT is 5, I guess this means that only 5 per, if I had to guess, it might be something like only 5% of the population in this specific region in Boston is below the poverty line, which is why we're seeing this sort of negative relationship. Then the model is predicting 29.05, something like this, right? Although what we would really like is that we also have some kind of confidence interval. Same thing for 10. For 10, we have 25. And for 15, we have 20. Which is to be expected. In what sense? The gradient is -5, right? We're taking a gradient of -5. Of -1, which means that if I go up by 5, I go down by 5. So 5, 10, 15 results in 30, 25, 30. 30, 25, 20 is what I meant. So it should be very clear that the line that we have fit, the line that we have fitted is this one over here. That's the line that has been fit. Okay. Let's see how we get these confidence intervals. Apparently, if I just look at the book, 3 parentheses, and then it asks interval, and we shall type, let's start with confidence. Confidence. So what is it saying over here? What's the difference between confidence and what was the second one? Let me check. Second one was prediction. Okay. So why don't we focus on, for instance, 10? We have between this is a really narrow interval, isn't it? It's between 29 and 30, whereas this is between 17 and 42. Let's have a look at the 17 and 42. Seventeen. 17 and 42. Something like this, right? Something like that. I guess this is some kind of error bar. I wonder what the calculation is. Are we... Hmm. And it's not centered at... It's not centered at the 25, is it? Who knows? Who knows? Might be something that we haven't done yet in this chapter. Okay. We will now plot median value and LSTAT along with the least squares regression line using plot and abline functions. So let's do it. We'll do the plot again. LSTAT and median value. But don't we have... Do I need to maybe attach Boston? And now we'll do abline our linear model. And there we go. That's the line we had earlier. There is some evidence for non-linearity in the relationship between LSTAT and median value. We will explore this issue later in this lab. The abline function can be used to draw any line, not just the least squares regression line. To draw a line with intercept A and slope B, we type abline A, B. Below, we experiment with some additional settings for plotting lines and points. The LWD equals 3 command causes the width of the regression line to be increased by a factor of 3. This works for the plot and lines functions also. We can use the PCH to create different plotting symbols. Next, we examine some diagnostic plots, several of which were discussed in section 3.3.3. So maybe for the time being, we'll skip this. And let's have a look at multiple linear regression. In order to fit a multiple linear regression model using least squares, we again use the LM function. The syntax LM regressing y on x1 and x2 and x3 is used to fit a model with 3 predictors. So don't think of that as addition, as in you're actually adding the values. It's still 3 separate predictor variables. The summary function now outputs the regression coefficients for all the predictors. So what are we regressing on? LSTAT and age. And we're going to save it as LMFit. So we're going to overwrite the previous model. LM. Give it your formula. So it's the median value. I wonder if we need to attach again. Regressing on LSTAT and age. Which data set? The Boston data set. Now we summarize. And here we go. Notice now that the age variable has a much higher p-value, although it's still considered usually in most contexts as extremely low. It isn't even a 1% p-value. These are our estimated parameters. LSTAT is still around -1. This is 33. And age is 0.034. So when we say age, must be the age of whatever, right? Either the property itself. Now that doesn't make sense because the data value is, I'm actually curious now. The age of what? Maybe the average age of the properties. No. The proportion of owner-occupied units built prior to 1940. Okay. So it gives you an idea of how recent the buildings are. The Boston dataset contains 13 variables, and so it would be cumbersome to have to type all of these in order to perform a regression using all of the predictors. Instead, we can use the following shorthand. So if you write a dot, that means you're going to take all the variables other than the response variable. Something that's entirely new to me as well. So lm fit, lm median value dot data Boston. There we go. Let's summarize. How many estimated parameters are you expecting? Well, you're expecting 14 because you're expecting a parameter for each of the 13 predictor variables as well as the intercept parameter. Why did I summarize Boston? lm fit. Here we go. These are all our estimated parameters. And you'll notice that some of them don't have any kind of code next to them. And this one's actually quite close to 1, which is in a way kind of, I guess age, if you actually allow for more variables, it's actually has no bearing on the median value. What else interesting to look at? This is the F statistic, 108.1, with a p-value of, it's for all intents and purposes 0, meaning we do not reject. This was which null hypothesis? The null hypothesis that the response variable is not related to any of them. That would be the F statistic in this case. We can access the individual components of a summary object by name. Hence, summary lm fit $r dot square gives us the r squared. And the same thing gives you the residual some the residual was it standard error? Yeah, the residual standard error. So let's have a look at that. What do we type? I think it's summary, ln bit, and then dollar. Could you do view? If you do view ln fit, what happens? Oh, you get them like this without, so you get to see all of them. Now, where is the? That's interesting. So if the book is talking about sigma, how would you know if the book didn't mention sigma? How would you know that there actually is sigma over here? It's interesting. Well, what if I typed names? I shouldn't be typing. Wait, actually, you can type over there, but but that's the same as what we had over here. It's just the left-hand column. So where is sigma? Where is sigma? How would you know that this contains something called sigma? None of these. None of these. It's interesting. Okay, but apparently, if you type this and sigma, it gives you your sigma. Sigma being the standard error of the error term, the epsilon. Which is this over here, right? The VIF function, part of the car package, can be used to compute variance inflation factors. Most VIFs are low to moderate for this data. The car package is not part of the base R installation, so it must be downloaded the first time you use it via the install packages option in R. So let's have a look. Let's see. So library car. Do I need to install it? It's interesting. Let's have a look. So we're installing this package. We're installing R. And while RStudio does that, we get these values. What if we would like to perform a regression? So we haven't yet explained. This is probably defined in the previous section. The variance inflation factor. Reading on, what if we would like to perform a regression using all of the variables but one? For example, in the above regression output, age has a high p-value. We already discussed that. So we may wish to run a regression excluding this predictor. The following syntax results in a regression. So you're doing the dot, so you're including all the predictor variables unless you type negative age. In that case, you remove age. Alternatively, the update function can be used. lmfit1, update your current model, but remove age. Now, interaction terms. This is where, and when we go back to the previous sections that we have yet to cover, this is where you wouldn't just want to look at the effect of the variables on a standalone basis, but you would also like to see what impact is there on the response variable when a specific value of a predictor variable is taken along with another value of a second predictor variable. Now the notation is that you write it as a multiplication, but you're not necessarily multiplying it. It's not primary school multiplication. It is easy to include interaction terms in a linear model using the ln function. The syntax lstat:black tells R to include an interaction term between lstat and black. The syntax lstat*age simultaneously includes lstat on its own, age on its own, and the interaction term lstat:age as predictors. It is a shorthand for lstat plus age plus lstat interaction age. Okay. Now, nonlinear transformations of the predictors. The lm function can also accommodate nonlinear transformations. This is because the data very often isn't linear or or doesn't seem to indicate that it's entirely linear. We haven't done it yet, but when we were scrolling through the pages yesterday, and I'm trying not to look at anything before we do the session, so that it's just as new for me to a certain extent as it is for everyone else. I would imagine when we come to page 91 over here, what we're looking at right now, assuming that I am actually sharing the book, and it would appear that I am doing so. The orange linear model isn't necessarily doing the best job of, this is a different data set. This looks like we're looking at the automobiles data set. And you may wish to take a polynomial of a higher degree. So we have blue is quadratic and green is a quintic relationship. This takes us back to when we first started this book, chapter 2, where you're trying to balance biasness and was it flexibility? I think those are the two considerations, and you can never minimize both of them. It's like a balloon, and you squash it from one end, but the other end gets larger. Although there is an optimal way of balancing them such that you reduce the test mean square error, if we still remember what that's all about. Okay. So we might decide it's a good idea. I'm kind of using a pincer movement on this chapter where we did the first few sections, but now we're working we're working a bit in the backwards direction. So the LM function, so the linear model function, can also accommodate nonlinear transformations of the predictors. For instance, given a predictor x, we can create a predictor x squared using I. I wonder what that stands for. I of x squared. The function I is needed since the hat has a special meaning in the formula. Wrapping, as we do, allows the standard usage in R, which is to raise x to the power 2. So you're transforming your data. You may remember, I've actually done some questions in summer, those of you who are following the more than once a week lessons, where we were doing an intermediate paper, and we actually had data, and it's tested quite frequently at intermediate, where you transform the data using some kind of log transformation in such a way that now the data or the log of the data plotted on the two axes follows a linear relationship. Okay, I'm kind of skipping this section. Qualitative predictors. We will now examine the car seats data, which is part of the ISLR library. We will attempt to predict child car seat sales in 400 locations based on a number of predictors. The car seats data includes qualitative predictors, such as that variable, which is an indicator of the quality of the shelving location. That is the space within a store in which the car seat is displayed at each location. The predictor shelf location, and this is qualitative, right? Takes on 3 possible values: bad, medium, and good. Given a qualitative variable, such as shelf location, or generates dummy variables automatically. And I wonder what dummy variables means in this context. Below we fit multiple regression model that includes some interaction terms. So let's have a look. You're taking your sales and you're regressing on all of the remaining variables, remaining in the sense other than sales, together with the following predictor variables: income as it interacts with advertising, and price as it interacts with age. We could maybe finish with this if we do it quickly. At least until we get to the... I'll just clear everything. So library ISLR, and we're going to do the... Just type it over here, ISLR, and we're going to take car seats. So data car seats, the usual structure to get an idea. And here we go. That's that. I'm going to do LM. Your formula is sales regress on everything, together with, now I need to copy, income. I wonder if this is going to work. I probably need to attach the income interacting with advertising, and I'll type the rest later on. Data is car seats. I expect an error. And that's odd, isn't it? Why didn't we get an error? Shouldn't I have attached? Anyway, never mind. And price with age. Let's save it as lmfit. Take a summary of lmfit. Just comparing to the book, just see that we have the same kind of things. These are your residuals. These are these. And I actually think we're going to stop over here. You have your residual standard error. We have 38. This is interesting. Didn't we have 400 observations? Why is it 386? Do you deduct 2, and do you also deduct the number of predictor variables? That might make sense, right? That would probably take you to around 386. Notice that we have a parameter for income interacting with advertising and price interacting with age. And although this one doesn't seem to be really contributing to the predictability of the model, you do get 2 asterisks over here, so it's statistically significant. It's slow, but the standard error is kind of in the same ballpark in terms of orders of magnitude. So you actually get 2.698 when you divide, which gives you roughly 1% in terms of a p-value, which is why we have 2 asterisks this time around. Okay, let's stop over here.